Hello, I'm Jordan, an application engineer at Materialise. In this tutorial, I will show you how to analyze the centerline of the aorta using the updated centerline tool in Mimics Core 28. We'll go step by step through the process of fitting, refining, and measuring a centerline, as well as exploring the features of the improved centerline tool. The centerline tool calculates the central path through a tubular anatomy. You can measure geometric properties along the line, visualize branching patterns, and export these measurements for further analysis. This tool is commonly used in cardiovascular and pulmonary applications, but it works for any solid anatomical part that has a tubular morphology. For our example, we'll use an aorta model created from segmenting the blood volume within the artery. Remember, if you use a hollow model with only vessel walls, the centerline will be computed inside the walls rather than within the lumen, so it's important to work with a solid part. To start, go to the Analyze menu and select Fit Centerline. You'll see that there are several parameters that you can adjust for this tool. When deciding on parameters, keep in mind that this tool works in a two-stage process. In the first stage, you'll set initial parameters for centerline calculation. And in the second stage, you'll be able to view the computed centerline in the 3D viewport and fine-tune smoothing and branch filtering in real time before committing. To begin the first stage of the process, let's set our parameters for the initial centerline calculation. Looking at the post-processing parameters, we will first see smoothing, which controls the smooth factor of the centerline. Smoothing will stop when one point in the centerline branch deviates from its original position by a distance greater than the smooth factor times the average branch radius. If that's confusing, just remember that a higher smooth factor results in a smoother centerline with lower variability in curvature. The default setting here is 0.3, which will offer a good balance between precision and smoothness in most cases. In extreme cases, where there are very short turns in geometry, you may want to choose a lower smooth factor. Next, we see branch filtering, which removes branches shorter than the specified length. Setting it to 0 keeps all branches. The last post-processing parameter is the noise threshold parameter, which filters out small side branches caused by surface noise. While the allowed range for this tool is between 0 and 1, the usual range will be between 0.005 and 0.06. Ultimately, lower values capture deeper branches in small vessels, but may add noise. Be aware that this parameter is very sensitive to changes and can have a significant effect on the centerline quality, so it's recommended to use increments of 0.01 or smaller when changing the noise threshold. Moving on to the mode selection, you'll see the option to choose between automatic or manual mode. The key difference deals with the resolving resolution parameter, which indicates the size of the tubular structures to detect. In automatic mode, resolving resolution is determined from the part's volume and surface. In manual mode, the user can specify the resolving resolution for improved accuracy or faster calculation. For this parameter, smaller values increase detail but lengthen calculation time. Within manual mode, you'll also find an angle threshold parameter, which determines the curve interpolation and branch point positions, ultimately affecting the definition of the main branch. For this example, we will go ahead with the automatic mode. The final parameters to consider in this first stage of the Fit Centerline tool are the control point options. You can enable equidistant control point spacing to resample the centerline with evenly spaced points, which can help standardize measurements. Once your parameters are set, click Apply to perform the initial fit. Your initial fit will appear in the 3D viewport. For better visualization, adjust the transparency of the aorta in the Object Properties window. Now, we are in the second stage of the tool, where we can adjust the smoothing and branch filtering sliders to instantly see changes. If you want to modify parameters that are locked here in stage 2, you can always use the Reset button to go back to the first stage. When you're satisfied, click OK to add the centerline to your object list. From here, you can perform further operations on the centerline, which can be found by right-clicking on the centerline in the object list. One example is the centerline post-processing operation, which lets you again preview and apply smoothing and branch filtering. Though similar, this operation is different from the second stage of the Fit Centerline tool, which allowed for fine-tuning based on the root or unsmooth centerline. This post-processing step will apply smoothing or branch filtering on the already generated centerline, which could allow for multiple iterations of smoothing to be applied. Another example operation that can be performed on a centerline object is the Edit Control Points operation. Here, you can edit the centerline just by clicking on one of the points of the line and dragging it into a new location. But most of the time, you'll just want to keep them in their original optimal position. Notice the checkbox to allow control point editing beyond part boundaries. This is new to Mimics Core 28 and enables moving points outside the object surface, which could be useful for simulating catheters or stents that may straighten vessels. Depending on the model and centerline at hand, you could apply a combination of the available operations. In this example, I may choose to adjust the branches coming off of the aortic arch to extend further into the arteries by using the operation called gross segment of the centerline. Here, we'll just select the segment that we want to extend with our first click, and then with our second click, we'll select where to extend the branch segment. We can also see a branch in the aortic root that was included in this centerline calculation. I'm more interested in the tubular structure of the aorta in this case, so I'll go ahead and remove this branch. Removal of portions of the centerline could be done in the Delete Centerline Part operation or within the Edit Branches tool under the centerline properties. Here, we can see a full list of all branch sets and segments. I'll go ahead and locate the unwanted branch segment on the 3D model and then delete it from the Edit Branches dialog. Once satisfied, select OK to apply changes. It's clear that there are a lot of advanced tools that you can use to refine the calculated centerline. If you want to do a measurement on the centerline, go to the Measure menu. Here, you'll find tools for the several different measurements that you can make. We're going to try out the best fit diameter measurement, which allows us to take a local vessel diameter. Take your mouse and click on any point throughout the centerline, and the measurement will appear in the viewport and the object list. We can also measure things like tortuosity. This works by simply clicking a starting point and ending point, and it will measure the tortuosity between those 2 points. If you're unsure how to calculate the measurements, you can look it up in the user manual under the Help menu. Now let's say we want to take centerline measurements throughout an entire branch. There's a much faster way to do this than by just working with individual points. Click on your centerline and again find the Edit Branches tool under the centerline properties where you can choose the branch to measure. We'll choose the main branch. Now click Export and select the measurements you're interested in. Finally, specify your output directory file name and hit Save. This will export a text file listing the selected measurements at each of the control points in that branch. If we open up that text file, this is what it looks like. You can see there is a legend at the top to help you decipher the document. It's showing the coordinates, the tangent vector, the normal vector, and the binormal vector of each of the control points. And finally, it shows the desired measurements. In this tutorial, we learned how the updated centerline tool delivers enhanced accuracy, a streamlined 2-stage fitting workflow, and powerful interactive refinement and measurement capabilities. Mimics Core 28 also introduces the new Fit Centerline Python API, which makes it possible to automate every step of your centerline fitting process through the scripting module in Python. For more information on using Python APIs, refer to the scripting guide under the Help menu. With these improvements in mind, whether you're working on vascular planning, airway analysis, or any other tubular structures, you can now achieve precise results more efficiently and with greater control. Thank you for watching this video on the centerline tool. To learn more about Materialise software tools, see our Materialise Academy page.